Hendrik Weber. You'll be giving the third lecture in interacting particle systems and stochastic PDE.
Hey, thanks a lot. Thanks for coming back and to still be there in the third lecture. Just to go back to the outline of where we were. So yesterday I had I'm going through that yesterday anyway, but today we're going to talk about trees and iterated stochastic integrals. So let's perhaps just to warm up again, remind ourselves where we were yesterday. So I had introduced that Kac-Ising model, which was a variant of this Ising model where the interaction range is a parameter of the model. So you had this parameter gamma inverse, which is the interaction range, the idea was that every given spin I interacts with the local average on a domain of size gamma inverse around itself. So this was this local average, which we denoted by H. And then we looked at the Glauber dynamic for this, just defined as in the mean field case the day before. And we had again this convenient formula here in terms of which was quite nice because it was the self-consistent formula. We could express this jump rate just in terms of the H, and there was only the dependence on the sigma here in front of the tangent. And then we went forward and did this decomposition. We look at this observable, which now depends on K, because this is the local average of the field around the point K at time T. And we could write it as, it evolves from the initial position by according to some drift term here, which we could calculate explicitly, and the martingale. And of course, both of these now also depend on K here. So these are now functions that depend on space and on time. And we could calculate the action of the generator on this H explicitly. And we got this nice formula here. And we then used the Taylor approximation for tang to get something here that looked a bit already like a Laplacian. And then here's something that was a linear term, and then here a cubic term, and then higher order terms. And at the same time, we could analyze the noise strength of these martingales. So we could calculate these predictable quadratic covariations. And we had such a formula here that was looking at, so the noise at K and L, they interact with each other through the sites I, where jumps can occur. And they interact here through these kernels that connect K to I and I to L. And overall, this is just as in the mean field case, this was a small noise. So this picked up a factor gamma to the D in front here later on. Then what we did is we rescaled the whole thing. So we blow up the observable, and we look on large times, and we look on large space. And the calculation here was again very similar to what we had done in the mean field case on Monday. And we came up, we just had this extra parameter epsilon here that we could play with. And what we came up with is that we get non-trivial behavior that we would expect to have these nonlinear dynamics for this choice, very specific choice of parameters. So we had to accelerate the time in this way that depends on the dimension. And we had to blow up in a way that depends on the dimension. And we had to blow up space also in a way that depends on dimension. And just looking at this, these things could be satisfied in dimension 1 to 3, but clearly not in 4 dimensions. And the guess that one would make from this one was that we have to choose this inverse temperature as 1, which was this mean field critical value, but we could be going a critical window around that that is scaled here by this alpha, and alpha, of course, depends on the dimension. And then I went to the other side and I talked about the SPDE, so the continuous theory. So I first started in equilibrium, just like for the Ising model, where you now want to define formally this measure on functions or distributions, which is given in this, formally in this way, but I had said that you should interpret this as a limit of suitable lattice approximations. And in particular, I had told you that in dimensions 2 and 3, you need a renormalization. And then at the same time, I introduced sort of the Glauber dynamic here, or if you want the Langevin, I sometimes called Langevin dynamic here in this case, where you take this L2 gradient of this potential here, and then you take the canonical Brownian motion, which with respect to the L2 scalar product, which is space-time white noise. And again, I justified this on the level of lattice approximations, where this looks like here you have a lattice approximation of the Laplacian, here you have just a cubic term, and here you pick up exactly the same constant that you had also in the lattice approximation here. And then you have here this approximation to space-time white noise. And I think I discussed this a little bit. So on every side X, you have an independent Brownian motion, but quite important, if you want to have a non-trivial limit here, you have to actually blow them up pretty badly as as epsilon goes to 0. So this scales with an epsilon to the minus d over 2. Point-wise, space-time white noise is not a nice object. You have to always average it out over space. You cannot evaluate this noise at a fixed X. Which is, of course, is not surprising. It's just like, you know, for stochastic ODEs, you're not allowed to evaluate the dW at a single time. You have to integrate it over time. And then what I told you is we analyzed the scaling behavior of these things. And I told you that the linear dynamic was invariant under the scaling here for an alpha that is dependent on dimension. So in 1, it was -0.5, in 0, it was 0. Sorry, in 2 dimensions, it was 0. In 3 dimensions, it was +0.5. And then we saw that if we do this, perform the same scaling in the nonlinear equation here, then we pick up this extra lambda factor in front of the nonlinearity. And in particular, we're here concerned with the small scale problem. So we want to look at what happens as lambda goes to 0. And what this here tells you is that in dimensions 1 to 3, which are, well, in the called the subcritical dimensions here, this prefactor here goes to 0, and we would expect that it makes sense to, to construct solutions or to analyze solutions using a perturbative ansatz around the linear dynamics, which doesn't have this. And this is indeed one of the main philosophical, it's not always stated quite like that, but I think it's like it really happened philosophically very much at the core of what happened in these theories of regularity structures and power control distributions over the last years. And then the last thing I told you was our 2D result with Jean-Christophe a couple of years ago. It was this convergence result. And the only thing that I wanted to perhaps just repeat is that we see also this need for renormalization here, just like we did in on the level of the choice of the beta. But on the level of beta, it's actually, on the level of the equation, it looks scary because you have an infinite term. But on the level of beta, it's really actually not so scary. It just means that instead of choosing your critical window exactly around 1, you have the small shift of order gamma squared log gamma inverse in 2 dimensions. And in 3 dimensions, it was a gamma to the 6 over gamma cubed. So it is a gamma 3. So again, it's a very small perturbation. Gamma has gone to 0 here. And right, so this is what we're doing in the 3D case. So this is where we were yesterday. Is there any question about this? No? Everybody happy? Good. So then let's pick it up from here. Let me perhaps just start with a quick pointer to a bit more literature if you were interested in this. So, following at the time what we did with Jean-Christophe, there were a couple of extensions of that. So, for example, with Hao Shen at the time, we did a version where we look at also in 2 dimensions. All of these results on the slide are in 2 dimensions. And we looked at, the Katz version of what is called the Blume-Capell model. And what this just means is this is an Ising type model, but the difference between to the normal Ising is that we're also allowing the spins to go to 0. So we're not only allowing plus or minus 1, but the spin is also, if you want, allowed to be neutral at a given site. And that gives us an extra parameter that we can play with in this dynamic to choose how likely the spin is to go to 0. And then we looked at the appropriate scaling regime, and we could actually obtain even a phi to the 6 dynamic. So this means the SPDE, where we have d2 d minus Laplacian phi, and then you had actually minus phi to the 5 term here, and then properly renormalized. And this was even pushed a bit further by Massimo Ibati, who was a student with Martin Hara at the time in Warwick. And he actually generalized this to arbitrary 2 to the phi to the 2n models. So he looked at an even more general state space here, and he could play this game a bit further even. And also another reference that I had already mentioned on Monday is that we, the way I stated the result, this was really a convergence, if you want, of Markov semigroups. I did not tell you anything about the convergence of the invariant measures, because I had, which possibly might be the thing we were interested in most, because we were, I assumed that the initial data converges and then just concluded that then the Markov process converges, but the statement does not include a statement that, for example, if I start the process in equilibrium, then it will converge, because I mean, it didn't check that. And there was basically a tightness condition on the invariant measures was missing, and this was provided later in this also in this follow-up work by Martin with Massimo, and they proved the missing tightness, and then basically used our dynamics to characterize the limit. And I think this just, I mean, this is perhaps just to connect back to what I had already said on Monday. I think this really has a flavor very much of Stein's method, where you use generators of Markov processes to characterize measures. And so this was not a quantitative result. It didn't measure the distance in any way, but I kind of would find it fun to explore this a bit more. Good. Now, how do we go about proving such a result? So the idea is actually not so complicated. So I'm going to explain to you here an idea which we adopted from a very recent paper by Dirk Erhardt and Martin Heira. And but I mean, I think it's pretty universally usable. So what we want to prove is that, right? So we have this X gamma, which is or observable. It's the spin field. It's the spin field. We take local averages. We scale properly. And then here we have X, I call the solution of the renormalized SPDE. And we want to prove convergence in law of one to the other. So what does that actually mean? Well, by definition, convergence in law just means for all bounded and uniformly continuous test functions with respect to a suitable metric, which I will brush under the rug, we need to prove this convergence, right? So we need to prove that the expectation of this observable on the one process converges to the expectation of the observable on the same process. That's the definition. And I mean, it may be obvious and it's not surprising, but let me just stress for the moment that, of course, X gamma, this particle problem, and the limiting process are not actually naturally, I mean, defined on the same probability space, right? There's no a priori, no natural coupling between that. And okay, you can probably place some measure theoretic abstract nonsense argument to tell you that you can put them on the same probability space, but it's it's not naturally on the same probability space, right? So now, how would one go about doing something like that? And the idea, okay, it's not so complicated, but I like it very much. So let me walk you through it in a little bit of detail. So I'm going to pick an additional parameter delta, okay? And what you should think of is delta is much bigger than gamma. So delta, if you think about it, is fixed for the moment, and we let gamma go to 0. Okay, so delta is order 1 if you want relative to gamma. And now we introduce an auxiliary process, X, gamma, and delta. And this is the solution of this equation. So what is the difference to before? It's exactly it's basically as before. The main difference that I have done here is that I have put an extra regularization on my noise. So this was this martingale that came from the noise that came from the gamma Katz model. And now I just regularize everything on scale delta, and think about delta being, again, it's order 1 relative to gamma. So this is much more regular. And then I also have to do a delta that change the renormalization constant, and the renormalization constant now should reflect this regularization delta. Okay, so the delta now plays more the role of the epsilon, if you want, from yesterday. So that's fine. And the other thing that I've done here is in this approximation, I've trashed in this term X gamma delta, I've trashed the higher order terms, so the cubic and the, in the original equation, there was actually tanh, and I had just replaced it by the third order Taylor approximation. But of course I had to still, the higher order terms were there. I still had to prove that they were small. And now in this X gamma delta auxiliary process, I've just trashed them. Okay, so that's fine. And now the other process I want to also still introduce is an X delta. And this will be the solution in continuum to the equation where I've just taken my space-time white noise and I regularize it at scale delta. Okay, so I do exactly the same thing if you want in the continuum. I regularize my noise here. I take again a delta dependent constant. So the renormalization constant now in 2 dimensions will just blow up like log delta or log delta inverse. And in 3 dimensions, it will blow up like 1 over delta plus lower order term. But I mean, for fixed delta, this is just some number. And now what is actually pretty easy to show is that if you fix delta and let gamma go to 0, then you have convergence and law of these regularized processes. Okay, I have a proof. It fits here on the end of the slide, so it's really easy. So well, okay, it's a sketch of proof. So the first thing that is not hard to see is that our dm martingale converges to white noise. And that's essentially a consequence of a martingale CLT. So you the way it's set up, the predictable quadratic variation of these jump martingales approximate delta Dirac in space and Brownian motion in time. There the jumps are small, so proving this is really easy. Okay. Now, of course, the whole point. I mean, what makes singular SPDEs hard and why one has to work a bit is that typically objects are much too irregular and you're not allowed to do the operations that you want to do on this low regularity class. But now we have regularized everything at scale delta, but delta is for me is 1 for now. I mean, delta doesn't go anywhere, it's just a fixed number. So if you take the mapping psi and now you regularize it at scale delta, then this is essentially smooth. So there's, I mean, there's not essentially, it's a smooth object. And then the mapping that solves this, that associates to this noise, the solution of this PDE is continuous. And then it's, well, okay, I mean, I'm waving a bit my hand because it's still slightly different equations, but not so different. And then it's a consequence, if you want, of the continuous mapping theorem, right? If you have a sequence of random variables that converge in law, and now you look at continuous functions of these random variables, then the continuous functions converge in law. That's a completely trivial consequence of the definition. Okay, so there's a, if you write down the definition, if you don't know this anyway, then write down the definition and you check it, and it takes you 3 seconds to realize that this is true. Okay, so this convergence is pretty easy. So from here. But now that's not what we were interested in. We wanted to look at this quantity, right? So this is the not regularized quantity. But now let's just do a triangular scheme. So we, instead of comparing directly the observable on this Kac-Ising thing with the observable in continuum, what we do is we compare the observable on that with the regularized object at scale delta. Then we go kind of from the regularized at delta to the continuous regularized at scale delta. And then we compare to we do the same thing. We remove now this delta in the continuum. And what is now quite striking is, if you think about it, so these two objects here, they are naturally coupled because they're constructed with respect to the same noise, right? So here, I mean, if you want to construct this X gamma delta, you live naturally on the same probability space, you have the same martingales, and now you solve an equation with respect to that. So these things live naturally on the same probability space, and you see, whereas here I had taken absolute values outside of the expectation, here I can actually take the absolute values. I mean, they live on the same space, and I can certainly bound the difference of these expectations by taking the expectation of the difference with absolute value, right? I mean that's easy. And now here, on this thing here, I go, I live on different probability spaces, but that's fine, that we had dealt with already before. And now here I do the same thing in my continuum limit, where I look at, I mean, again, these things are naturally coupled. I have the same noise. Here the noise is used to solve the equation, and here the noise is used to solve the regularized equations. So again, I can just take the expectation of the absolute value of the differences, right? And now what you just have to do is you have to take limits in the right order. So the first thing that you do is you take the lim sub as gamma goes to 0 for fixed delta. And then you see, I mean, this is what we had just seen. This thing we had just seen goes to 0. This was the previous slide, right? Because for fixed value of delta, we have convergence and law of these regularized objects. This thing doesn't actually even depend on gamma, so that doesn't do anything to it. But of course, this thing does. And so anyway, now going to 0, this thing goes to 0 as delta goes to 0. And now in the second step, we now let the delta go to 0 after that. So what we have to prove now is only that if you take the lim sup of this quantity in first and then delta to 0 of this, and then here you only have to let delta go to 0, then this converges to 0, right? So that's all we have to prove. I want to perhaps, before I continue, just make this draw this analogy, which I like, and I find this very motivating. I find this has very much a resemblance to, I mean, if you are familiar with how large deviation principles are often proved for example, if you want to prove large deviation principles for solutions of stochastic differential equations, you have also these generalized contraction principles where you introduce auxiliary intermediate regularizations, and you have similar conditions that you have to check. So this is, for example, discussed quite nicely in Deutschland's Struck's book, and I mean, this was actually where I learned this for the first time, and I mean, this may not be the most complicated way of, most exotic way of proving convergence in law, also, but at least that's kind of what at the time inspired me to go about it this way. So the conclusion is now we need to prove only these convergences, and in particular, I mean, now we have a uniformly continuous test function f. And what is really sufficient is to prove now pathwise estimates uniform in gamma, right? So it's lim sup. I'm just going to bound it by a sup here. And so what we're left with, what we have reduced ourselves to prove convergence in law by just proving pathwise that these approximations, this delta approximation is close to the limiting equation and uniformly in our parameter gamma, which is the original limit, right? And I mean, let me just say, I mean, of course, why does this make our life easier? Because this is exactly the type of stability estimates, this kind of statements. If you look at the equation with a regularized noise and you compare it to some limit, that's exactly the kind of approximation result that the theory of regularity structures was really built to give us. I mean, this is precisely the typical output that you get of it. And in particular, actually, the second estimate that I have here is essentially the main result of Martin's original paper, that the first paper on regularity structures. This precise estimate for 5.4 and for the 5.4 dynamics in 3 dimensions. Okay. Again, let me just pause briefly. Is there a question? Is this clear? Milton. Oh, yeah, Milton is clear. I mean, I think it's perhaps interesting to compare this to other techniques to prove convergence in law to stochastic PDE. I find them quite different. If you compare this philosophy, for example, to these techniques, for example, that Milton and Patricia have introduced for converging of the KPZ equation with these Boltzmann principles, and I find them philosophically quite different. And yeah, and I mean, of course, these analysis that relies quite strongly on the fact that you know that the invariant measure is Gaussian, and then uses much more probabilistic tools, whereas here it looks much more like a numerical exercise, numerical analysis exercise, basically, right? So I mean, it's you will see in a minute that it's in a sense not a very probabilistic approach. It looks really more like pathwise analysis, and yeah. All right, so this is that. So now this is where the point where I have a good excuse to tell you something about regularity structures, but I'll try to not go too much into the technical details. But let me start with a bit of a philosophical point. So the main philosophical ingredient of this whole theory is this point called subcriticality that we had already seen yesterday. This idea that if you look at the solution on small scales, it should really be seen as a perturbation of the linear equation, and that then allows, that makes it even sensible to think about this as to make a perturbative ansatz to solve the equation using if you want a perturbation theory and the noise. And the analysis of an equation is always split into 2 parts, so the first and the second part. And the first one I call probabilistic step, and then the analytic step. And in the probabilistic step, one constructs an approximate solution using, again, perturbation series in the noise strength, and you truncate it after certain points. And I will go into that in quite a bit of detail later. And then in the second step, there's analytical analytic tools. So what you basically want to say is, after you have truncated this perturbation series after sufficiently many terms, then we can bound the error now using purely analytic tools. And the ingredients here, just as keywords, are regularity estimates for heat equations or Schauder type estimates, and the reconstruction theorem is one of them. So this is all used to bound the remainder. And I don't think I will really be able to speak too much about this whole side of stories, but just, I mean, to advertise, if you the slides, the web page that I used to put the slides, that so that you may already have found down there, there's quite a few slides on that for courses that I've given on regularity structures on the over the last years. So if you're interested in seeing those, then have a look. I mean, of course, there's many other people who have given courses on regularity structure. So if you prefer somebody else's courses, that's obviously your choice. But okay, this is one source that you may want to look at. And another perhaps more philosophical approach to compare this to the analysis of these problems using renormalization group. So I think if you look in detail at how these how this analysis works, I think it's often there's a certain amount of similarity. There's always a multiscale analysis somehow hidden under the hood of both techniques. And in both cases, you do a perturbation analysis and then have to work in order to say that the remainder is not so big. I think one main technical difference is that in this RG techniques, you don't necessarily have this strict perturbation separation between probability and analysis. So here we are pretty brutal. We do the probabilistic bounds, and then if you want, take an L-infinity bound over all scales and then put all of that into the analysis, whereas in RG you typically don't do that. And that makes, I think, some things in regularity structures a bit simpler. But one price to pay with that is that RG, I think, is at the moment still able to say something about critical theories, so that certain critical theories, not necessarily 5-4, whereas regularity structures as of now is not. So is this okay for philosophy? So what I want to do now, and mostly for the rest of these lectures anyway, is to focus on the first step, so the perturbative expansion. And kind of here, the rule of thumb is the closer you get to this criticality threshold, the more terms one needed and are needed. And for example, if you look at 5-4 in 2 dimensions, you need only these three terms. So you need what I call Z here, which we had already, I think we had introduced that before. So the solution of just the linear stochastic heat equation. So this is what you do the perturbative expansion about. And in this regularity structure business, it's become customary to actually denote these terms in the expansion by trees, just because if there's many terms, it's trees are kind of easier to keep track of what you're talking about, rather than we're calling objects Z1, Z2, Z15. So in trees, at least one sees still a little bit what's happening. The second thing we need is this Z squared, and we need a renormalized version of that. And I'll denote that by this. And of course, the intuition, which many of you will have seen already, is that this dot at the top corresponds to an instance of the noise, and this line here corresponds to solving the equation with that as right-hand side. And then here we have one noise, we solve the equation, and here we have a noise, we solve the equation, and then we multiply the two things. That's what this merging of these two lollipops at the origin kind of denotes. And for Z cubed is the same. Again, we need to renormalize it, and we need to, and this we denote by that picture. And for 5-4 in 3 dimensions, we're a little bit closer to criticality, so we need more trees, but it's not actually so much more. So we need these, if you want these additional 3 two-story trees, we need, well, this is just the weak cubed if you want, and then we integrate it up once more and then multiply it with this one. And here we need this is this object here, integrated up once more and then multiplied again with it. And this one is solving the heat equation with this right-hand side and then multiplying with this one. And I should also say that the extra logarithmic divergence that you have in 543 that you don't have in 542 comes from these two diagrams. So you have this leading order divergence, this log in 2 dimensions comes from here, and this is the 1 over epsilon in 3 dimensions, and you have this extra log divergence that comes from these two diagrams in 3 dimensions. And so the aim, actually the main task in our proof of convergence of Kac-Ising both in 2 and 3 dimensions was to mimic the construction of these stochastic objects that was done in continuum, for example, by Martin and others, and to mimic this on the level of these martingales that came from Kac-Ising, and then prove the required uniform and gamma estimates that I had already denoted before. So this is the step 1 of the analysis. Then there's the step 2 of the analysis, the analytic step, where you also have to prove something, but that's possibly a bit less interesting. So I will not talk so much about this. Okay. So before I now go into this a little bit more, so what I want to do is actually explain to you how this is done in continuum, and I want to perhaps first tell you what actually are the bounds that we actually need. But let's start before we get into it. Let's define an aim. And the first notion that I want to just introduce here is this notion of this. Of these local averages. So this is perhaps not so surprising, but let me do it anyway. So let's for a given smooth test function, we define this notion phi rescaled up to scale lambda around the base point x, simply by, well, you take phi, you rescale it, you move it, you recenter it around x, and then you rescale the variable to be small on scale lambda. So if this is your original function phi, then the rescaled function phi now the origin has moved to x, and now if the original function had height 1, now this new function has height lambda to the minus d and then width lambda. And of course, the point of the scaling is that the integral of phi is preserved. So this is the scaling that preserves the L1 norm. So in particular, if we choose a phi which has integral 1, then this is an approximation of delta. And if you test this against a nice test function, then this would just converge to f of x. And for distributions, so we will mostly deal with distributions in this lecture, actually exclusively. So then this convergence doesn't hold because distributions don't have pointwise values. But what actually it turns out to be quite a convenient way of measure, regularity. Actually, this is the quantity we want to deal with of objects by seeing. We look at this distribution T, and we look at the local average of this distribution around x at scale lambda, and we see how this blows up as we let lambda go to 0. And let me just tell you a kind of a cute example. If you just take your favorite distribution, could be the delta Dirac, then you test this delta Dirac around 0 at scale lambda. But okay, by definition, this is just this function here evaluated at 0, but multiplied with a lambda to the minus d. So this now blows up like lambda to the minus d, obviously. And so we would then say that the delta Dirac has regularity minus d. Okay. Is this okay? Sorry, I keep insisting on this because I really see you on a tiny window only. And I cannot really see if you're all sleeping or telling me that it's boring or I should speed up or slow down.
I think we're good. Everyone happy? Yeah, lots of nods. We're good, thanks.
Are you happy with delta Dirac having the regularity minus d?
Looks like yes.
Well, then you should. Okay, then you. Then if you're happy, then let me ask you why is it? It's because it's also true that delta Dirac in d dimension is actually in the fractional Sobolev space of order minus d over 2 minus. So how is that consistent? What is important with this? This is an L infinity-based way of measuring regularity. This is if you want the Hölder space of regularity minus d, and this would be the L2-based space of regularity minus d. And delta Dirac. For delta Dirac, it depends very much in which integrability you measure the regularity. If you measure in a fractional Sobolev space with integrability 1, you would actually only have regularity minus epsilon. Anyway, this is, I'm not sure if this remark was worth it, but anyway. So, but this is just to say this notion of regularity.
So Hendrik,
yeah.
Maybe you can remark that for white noise doesn't matter.
For white noise, that's correct. That's an interesting point, actually. For white noise, you have the bound in L infinity, but that's the same for Brownian motion. That's but that's an important that's something that plays a big role here. I agree. So the for all these Gaussian distributions that we're dealing with, the regularity measured in L2 or L infinity or L1 is always going to be the same. Sort of, but you know that, for example, if you look at for Brownian motion, so for Brownian motion, you know that it's in regularity C1/2 minus, but if you were to measure it, for example, in an L2 based fractional Sobolev space, you would also only go to H1/2 minus. So even though you measure kind of in a weaker integrability way, you don't gain extra integrability, which is very different from the delta Dirac. Thanks, Milton, for giving me an excuse to talk about this kind of analytic excursion. Okay, so let's just go to the aims list. So what we want to show here actually, what we need is these kind of moment bounds on these objects. So we will need in the end to look at this. So Z is this linear stochastic heat equation, and we will probe it around point X at scale lambda. And now we take second moments of that. Well, I just for scaling reasons, I put it a half outside. And we will need in 2 dimensions here a log lambda inverse, and in 3 dimensions we will get here lambda to the -1/2. And let me just stress, I mean, you may not remember that, but yesterday we had talked about the scaling of the linear stochastic heat equation. You may remember there were these scaling exponents that are called alpha. And I told you that this was the same as what I would call the regularity. And this scaling exponent was +1/2 in 1 dimension, and was 0 in 2 dimensions, and was -1/2 in 3 dimensions. And this is exactly the same as you have here. So this -1/2 that you have here is exactly this the -1/2 that we had in the scaling exponent alpha yesterday. And this log lambda here is exactly the 0 that we had in the 2-dimensional case yesterday. Okay. And so this is the first estimate that we will need. That we will need, and for the square here, and it's a renormalized version of the square, and I will come to that in a minute. We will need again the same. We probe this at scale x around x at scale lambda, and now in 2 dimension we will have that log the same thing squared, and here -1. So this means in 3 dimensions this will be later a distribution of regularity -1, just below -1, and then we will need the same for the cube, for example. And for 3 dimensions, we will also need higher order trees, but I didn't want to write down this precise statements here. And so the aim of the game is, I mean, these bounds in the continuum again in 2D, they have been proved a long time ago. And in 3D, they were, for example, proved in Martin's paper, in Martin's original paper on regularity structures, just as these higher order trees. And the aim of what we wanted to do is now to basically mimic the continuous proof and just replace the white noise and the Gaussian analysis by this analysis of these jump martingales. Okay, let me just also briefly, I have here this side note where I say for these particular trees, this just for the regularity is the same as the order. Okay, I should have perhaps not made that remark, but it's just for people who know about a little bit about regularity structures, that typically one actually has this positive renormalization, this recentering operation. But for these 3 trees, I don't need to do that. But again, I mean, if you look, for example, at these other lecture notes that you find on the same webpage, then you will have a lot of discussion of this point. Okay. Good. So now I want to actually tell you how you can go about analyzing these kind of Gaussian, or polynomials in the Gaussian. And the keyword here is going to be that we're going to represent these polynomials in the Gaussian using iterated stochastic integrals, or equivalently the Wiener chaos decomposition. The Wiener chaos decomposition was certainly not invented by Martin, but in this context he used it, at least to the best of my knowledge, in this particular form for the first time. And I want to show you that. But before I go that, let me just briefly touch again on this notion of white noise that we had already talked about yesterday. So yesterday we had actually introduced this white noise Xi in two different ways. So once I had given you this lattice approximation, which was you take for every lattice point, you take an independent dB, so derivative of Brownian motion, but then you blow it up quite a lot with this epsilon to the minus d over 2. So this was this natural lattice approximation to space-time white noise. And I had told you that this is the same object if you take the spectral approximation. I mean, this is the one-dimensional version, but you can on the one-dimensional torus or on the circle. But of course, you can do the same thing in higher dimensions. Or you can take your favorite orthonormal basis of L2, and you can do the same thing. And I wanted to actually write a B dot here. So this would be a spectral approximation to the same object, but that's not the way we want to work with it today. So the proper property that I want to use here is this definition: a white noise over, say in time and space over the torus, but it doesn't really matter what domain you pick here. You could put actually an arbitrary sigma finite measure space here. Is a family of centered Gaussian random variables, which are indexed by smooth, or I mean, actually, even they don't even have to be smooth. They can just be L2 test functions on here, such that this identity here holds. Or sorry, this is not over this interval. This should be over RT and over the torus dx dt. Okay, so that you have this isometry. And two exercises is just, formally, this is just the integrated version of this identity, which you may see, which you may see more in, say, the physics literature. So the covariance formally between the white noise at t and x and the time t prime and x prime is given by these delta Diracs. I mean, this formula, of course, doesn't make sense as it's stated, because I'm not allowed to evaluate white noise at points, and certainly the covariance of two random variables cannot be a distribution. But how you should interpret this is if you take this formula sort of as face value and then integrate it against test function and then close your eyes and are optimistic about the calculation, you come up with this formula. Okay, and this formula, of course, does make sense. Perhaps just quickly, sorry for keep doing that, but again, is this something that you're familiar with and comfortable, or is this something that is very awkward? So let's start a bit with the analysis just of the linear thing. And what I want to do here is I want to make my life a little bit easier. I'm going to work on the full space that makes the formula slightly nicer. And I'm going to introduce a massive term. So I'm going to not just look at the heat equation, but going to put this extra massive term here. This is just to make sure that integrals converge at infinity, and I don't have to worry so much about that. It's not really essential. And so if you look at, but for example, it allows me also to solve the solution at minus infinity and look at stationary objects, which is a bit nicer. So if you do that, then basically if you believe in the standard variation of constant formula, then you get the solution formula. So this Z here can be written as the white noise here. You have the noise at time s and times y, and then it's propagated with this kernel to t and x. And this kernel here is just the Gaussian heat kernel. So here's just the standard heat kernel for the heat equation. And then you have here this extra e to the minus m squared t term that comes from here. Again, I mean, this is a nice way of doing it because it gives me something which is stationary in t and x. I mean, again, this is a slightly formal expression because, of course, again, I'm not allowed to really write down this Xi evaluated at given space-time point. But if you put a test function in the right point and they're in the right places, then this is fine, and I'll leave it for you to fill that in. And now we can just calculate actually the variance that we need to do. So let's say what is actually the expectation of this variable z here against some test function phi squared. Okay, so what we do, let's just double the variables. So here I write the z tested against phi. I integrate the test function of the phi. Here's the kernel, and that kernel connects to the z, right? So this is one of them. This is just basically plugging into the formula that on the previous slide. And then as I have a square, I'm just going to double my variables and I'm going to write it again. And the only thing that I want to do here now is I want to introduce new names for these variables. So instead of calling it Z0 as well, I call it Z0 bar, and here Z0, well, same Z0 bar, but I just put bars over all the variables. So that's not so crazy. And now, okay, I'm a bit optimistic, so I think I hope I'm allowed to do what I want to do. So which means I put all of these integrals just on front. And then you see that almost everything here is deterministic. This is deterministic, this is deterministic, this is deterministic, and this is deterministic. So I pull all of that out. And then I have to only take the expectation of the only stochastic bits that are there. So these are the stochastic bits. And now I use my formal identity that I have a delta Dirac function here. And then I come back with this formula. Okay. I mean, of course, again, I'm cheating a little bit because I mean, I'm not really allowed to use this kind of Fubini type theorem for distributions. But if you interpret it with test functions in the correct way, then you see that it's fine. It's just that I find it actually more intuitive to do the calculation this way, and then after convince myself with test functions rather than doing it with test functions right away. So I'm only going to show you this one. And what you see here now is actually something which I find quite striking in this business, and I would like to emphasize this a little bit, is that, I mean, this calculation works, and the answer is true in arbitrary dimensions, okay? And one of the striking point here is, even though this thing in higher dimensions is going to be a terrible irregular distribution, I still have actually this well-defined notion of a covariance function, which is smooth off diagonal. Okay, so this is, I mean, this function is going to be a smooth function away from the diagonal when the Z0 is away from Z0. Okay, I mean, it's well known, but I still find it very striking. And I mean, here actually we can actually even calculate it, at least if we kind of put the variables for the same time. So let's actually calculate this thing. For the moment, let's just put them at the same time. So one of these spacetime variables is 0x0, and the other spacetime variable is 0x0 bar, right? Here's just a reminder of what the kernel was. Then this, and then now I've just written this integral, which is a space-time integral. I've written it as I've just made it explicit again that this depends on the x variable and on the t variable. And then you see that you can actually, I mean, this is except for this this e to the minus m squared term here is just a Gaussian heat kernel. And in particular, you see if you do this x1 integral, this is just the convolution of two Gaussian kernels. And you know that the convolution of a Gaussian kernel gives me again a Gaussian kernel, and I just have to add the times. So what this gives me here, if I do this x integral, is just this. And I mean, this is sort of, if you want, let me do it slightly formally, e to the 2 Laplacian at t x0 minus x0 bar and times e to the minus m squared t. And so if you do this integral, then you get, I mean, either you just formally believe that the integral here just gives you 1 over Laplacian minus Laplacian plus m over 2, because clearly e to the minus alpha t integral from 0 to infinity dt gives you 1 over alpha. But if you think that I'm cheating because I'm doing this with operators, well, I mean, you can justify this, for example, doing it in Fourier space or seeing which equation it solves. So what you get is actually that this is a very explicit. You can calculate this integral. It's a semi-explicit function. It's the so-called Bessel potential. It's the kernel for this operator here. Okay, so this means that if you convolve a function f with this kernel, then you get the solution of this equation. Sorry for keep doing it, but is this again crazy or trivial?
Looks okay.
So okay means not in the right pace, or I mean, are you happy with these kind of integrals with these operators in the exponential, just putting a 1 over? That seems pretty dodgy, no?
Yes, but I think we're okay.
Yeah, okay, fine. If you don't criticize me, I mean, I remember I saw these kind of calculations when I was an undergraduate in my physics class, and I was always going crazy with the. I mean, mentally, I was super annoyed with the professor for just, well, you have e to the Laplacian, you integrate, you get 1 over the Laplacian. I found that horrible, and now I'm doing the same, and nobody's complaining.
We have a question in the, or a comment in the chat.
Yeah.
You're missing a power 2 on top of m, but that's a minor point.
That is very possible. Yes, I am. Was that the one?
That's the one.
Yeah, okay. Okay, good. Yep. So then let's not. So I mean, so this this function is actually still pretty explicit in one dimension. It's just that. So this g of x is 1 over 2m e to the minus m absolute value of x. So you see, you have this this characteristic behavior here. It's a Lipschitz on the diagonal, and then it has this exponential decay. And so this means actually that if you fix your process t, then this this object in the variable x, if you treat kind of x as the running variable, then this is just an Ornstein-Uhlenbeck process. So this is the covariance function actually of an Ornstein-Uhlenbeck process. And in dimension 2 and higher, it's not completely explicit, the formula, but we understand perfectly well what the asymptotics are. So for small values of x, this behaves proportional to log x, so the behavior of the Newton potential in 2 dimensions, and in 3 dimensions or higher, you have this, well, again, like the Newton potential. And but different from the Newton potential, because I have this m squared term, you have this large scale behavior, which is like e to the minus mx. And I mean, this has of course a name. So this object zt of zt with x as the variable is actually, it has a name. It's called the massive Gaussian free field in d dimension with mass m squared. Okay, so this thing we understand pretty well, so that's fine. So now, how about this these objects z squared and z cubed, and how do we analyze them? And I would, in principle, like to do just a Fubini type theorem. So I would like to see, well, I mean, z squared, z was just given by this convenient integral of k xi dz. So why not just use a Fubini theorem and write this as well, as a double stochastic integral of this type if you want. But what we will see now, or I mean, or know already for many years, is that one has to be a little bit careful when doing that. And I want to actually now spend a bit of time doing a detour on reminding you on some basic Maldiavan calculus on iterated stochastic integrals. And I'm going through this in a bit of detail now, because the bulk of our work in this 3-dimensional paper is to basically adapt this this continuous decomposition of polynomials in the noise, and to adapt this to the case of these jump martingales. Okay, so I want to explain to you first how this works actually in continuum and kind of when the world is nice. Okay, so this is actually a detour of, again, possibly quite standard material in stochastic calculus. So this is basically, you can read this, what I'm going to have in this next few slides in, for example, Noah Lard's book or this book by Kuo. And so I'm going to be even a bit more general than before. So I'm going to say Xi is a white noise now over, actually, if you want, some arbitrary measure space. And the only thing I will assume is that my measure is sigma finite and non-atomic. So this just means that I have a bunch of random variables which are indexed by L2 functions with respect to this measure, and I have this identity. Okay. I mean, of course, in reality, I'm interested in the case where this is kind of space-time, or but I mean, this all I'm going to do now works on arbitrary measure spaces. And so for any measurable set, I'm just going to say, well, okay, the noise on that set A, so this is just a shorthand for Xi tested against the indicator function, okay? And if you now make this definition, then you, of course, get immediately from here that kind of the expectation of Xi of A squared, so is mu of A. So typically the magnitude of that random variable on a set of measure A is square root of that quantity. And it has the nice property that, of course, if you take disjoint sets, then these are, I mean, they're uncorrelated by this identity, but as everything is Gaussian, that means in particular that they're independent. And in addition, if you have a pairwise disjoint or disjoint things here, and such that the union here is a finite measure, then you actually have this identity here in L2. Okay, so this in principle looks very nice, and it suggests that you have, I mean, it almost looks like you had a random measure, but it really plays a role that these identities here hold only in L2, and actually pathwise it's not at all a measure. So, and that we will see in a minute. And now let's just define if you want, double stochastic integrals, and we do this in a relatively easy way. So we want to, the aim is for a function that depends on two variables, real valued. We want to define this double stochastic integral, okay? And okay, we use this notation for that. And the idea is to just, as normal for integrals, you define them by approximation with piecewise constant functions. And we're going to do this like that. We're just going to kind of, I mean, we're going to tile our space into these sets. And or say we take an elementary function which has this property that it's the kind of adapted to a tiling like that, and has some values here. I mean, this is a deterministic function, so there's no issue of adaptiveness or anything. And the only really major restriction that we're going to make here is that we are going to assume that this is 0 on these diagonal squares. And this is going to play a big role later on. So for such an f, which is, if you want, elementary in that set, we're just going to define it as we would if this were really a measure. So what we're just going to do is we're going to sum over all of these pairs of tilings, so I and j. And important, of course, the diagonal doesn't matter. So there is no contribution here if I is equal to j, and then we just take this fij times this, if you want, this product measure of this set. So for example, for this one, you just take if you want, the measure of here times the measure of here, right? So this is how you would define a product measure, if a product integral, if it were a measure. Okay, so now fine, this is our definition. Now let's just calculate stuff with it. So the expectation, first of all, so expectation of this is 0, and that's pretty easy to see. If you just take the expectation, well, that's equal to the is equal to the sum over all pairs of tiles. And then you take here this Fij, which was deterministic, you take it out, and then just the expectation of these things. But these were different, right? The tile I is different. I mean, the set I is different from J. By assumption, there's no contribution where they're the same. And so this disappears. And here you start to see why it's important that you make that assumption, of course. Right, because the expectation of each of them is 0 and they're independent. Yeah, I mean, of course, this is still not a Gaussian random. It's not a Gaussian random variable because it's a product of Gaussians, but yeah. And now let's calculate the covariance. Well, okay, fine, no problem. Well, without loss of generality, we can always assume that they are that these functions f and g live with respect to the same partition. We can otherwise just make it finer. And then we have now this quadruple sum here. And then we have the Fij and the Gi prime J prime. And then here we have this fourth, we have here this fourth order, this fourth moment of a Gaussian. And so here, what we're going to do is we're going to use, so wait, I think I screwed up the slides a bit. So I'm going to use, well, anyway, you probably know this identity that I have already here. So if you take, that's what we're using here. If you take the fourth moment of centered Gaussians, then you have this identity with pairings, right? I'm going a bit quick, but is everybody happy with that? So I'm not going to explain this because everybody knows that. Okay, good. So I'm just going to use this here. So I use the pairings, and I never have to pair this with this because they are 0, right? So I just have to pair this with this, and this with it, and this with this. That gives me then this term, and I have to pair this with this, and this with this, and this gives me this term. So if you plug this in, then you get this identity here. So so what we have is some sort of almost isometry. So we can write this as the this covariance here can be written as this L2, if you want, inner product with respect to the product measure here of these two functions. And here you just have the L2 product where you have just swapped the variables. So here you, instead of Z1, Z2, you just swap them around, right? So this is what you get if you do the pairing kind of this way around. So you get the same thing, you just do the pairing otherwise. So wait, then this Wick theorem we don't need because we just saw this. And in particular, if we look at this for symmetric functions, which means that this flipping of variables doesn't change it, and which are and which is 0 on the diagonal as before, then we have the super nice isometry property. So this the second integral with respect to this symmetric function, the expectation or the variance of that thing is actually equal to this L2 with this L2 in a per scalar product with the combinatorial factor 2 in front. And now from here, we're pretty much done with our construction of these integrals, because we had assumed that our original space was non-atomic. So this means that the symmetric and piecewise constant functions, which are 0 on the diagonal, are actually dense, at least in the space of symmetric functions. So we can approximate all functions, even if they're not 0 on the diagonal, we can approximate them by functions that are 0 on the diagonal in the space. And this means then that we can so this again, as this uses the fact that the measure is non-atomic. This means we can extend this notion now to all symmetric L2 functions on the product space, right? So this is clear, and so this means in particular. And so from here, you can actually go one step further, is you can actually define this also actually for non-symmetric functions, but then you don't have an identity here, but you have just an inequality, but that's also fine. Okay. So this is the definition of the iterated of the second stochastic integral, and you this nice isometry from the with the L2 space. And of course, this is just a special case. You can do this now in n variables. And you can call Hn the image of this now n-fold symmetric L2 space under In, and this is this integral In is an isometry up to these combinatorial factors n factorial then between this symmetric space and this well Hn is the image. Well, that's the subset of the probability variables, and this is called the nth Wiener chaos. And one property which is not so hard to show actually now is that these Hns, if you take them for different values of n, they're orthogonal in this space. So every random variable in one Hn is uncorrelated from any random variable in an Hm for another value of m. And in particular, you have that all random variables on this L2 Gaussian space can be written as a sum of all these things. So this is actually an orthonormal decomposition of our space of all random variables. Okay, so every L2 random variables over the Gaussian random space can be written in such a sequence of iterated stochastic integrals. And I mean, this is of course a famous result, so that the L2 space over a Gaussian probability space is isometric to this direct sum of the symmetric space, and this is actually called the bosonic Fock space. So this is something that again is extremely well known. Again, I think this was fast for it would. Was I being too fast, or was I being too slow, or you all know this since kindergarten, or? I mean, I learned this when I was a PhD student. I'm not sure how it is in the audience.
I don't think it's too slow, but people look happy.
Sorry for putting you on the spot with always the same question, but it's really a bit odd for me to I see you with a screen where on my screen the whole audience is about 1.5 centimeters times 2 centimeters, and we're all wearing masks, so it's very hard for me to gauge your happiness.
I sympathize. We can keep communicating. It's good. Yep, we're happy. Thanks.
Okay, good. Okay, good. So this is this decomposition of all random variables into iterated integrals. But now, how does one actually deal with this in practice? So what we want to do is now we come back to this Fubini type situation that I wanted to say. So I start the aim, right? I mean, the aim that we had actually with this whole, I mean, okay, so why is this useful? This is useful because I have an isometry. If I have such an iterated stochastic integral and I want to calculate its variance, I only have to calculate the A2 norm of the kernel, right? So this is the aim of the game. So I'm using this to calculate variances, to reduce the calculation of variances to the calculation of A2 norms, and basically to calculate integrals of kernels. Which I will then do later. And so the question is now, how do I get for a function which doesn't a priori come as such an iterated integral? How do I get this? How do I get this representation? I know by this abstract theorem that I had on the previous slide that this always has to be possible. But the question is, how explicit is this? And well, I mean, let's just do it. I mean, for example, we were looking at this situation where we have the z was, for example, given by such an integral here, where this f, the test function, was this kernel that we had called k. And now I want to, for example, understand what the square of that thing is, right? This would be the Wick square. And so now let's pretend for the moment that f is, I'm interested, of course, not ultimately interested in elementary f's, but let's just say for the moment I can of course approximate then later by an elementary f. So let's just look at this thing. But now, okay, now this thing here, which is the integral squared, is of course now I can now just double the variables. This is the sum, this double sum. But here, I mean, if I square this thing, there's no reason at all for terms on the diagonal to disappear, right? They're there. I mean, they're not zero. So they are there, but because, I mean, if you view this now as a function, you double the variables, you view it as a function of two arguments, there's absolutely no reason why this should be zero. I mean, and actually it's never zero on the diagonal. It just cannot be zero on the diagonal. It's just the f squared on this box 4, right? So this is just how this would look. So this does actually not have the form that it should have as an approximation for a stochastic for this double stochastic integral. But it's fine. I mean, I'm just going to decompose it. I'm going to call 1 the bit that cuts out these bits, and I'm going to put these things here. And here I'm just going to put this this Gaussian, if you want, Gaussian measure squared. I mean, this is of course an exact identity, so there's nothing to argue about it. And now these terms here, they behave quite differently. So if we now kind of say, well, our original f was actually not elementary, so we want to now pass to a limit where we approximate a real f by some elementary object, then this thing will indeed converge to stochastic to this double stochastic integral, which we had defined here. So this will just be the double stochastic integral of the function f, well, tensor itself, which means you have, right? I mean, this is just the function f of x times f of y. Actually, I've written it even here. So this is this will really be what you would guess if you naively apply the Fubini. But now here on the diagonal, of course, it's quite different. So this thing does in general actually not disappear. And you can see already, I mean, this is now the square of a Gaussian. So this certainly does not have expectation 0 anymore. And I mean, the expectation of this thing is, for example, now mu of AI. And it's a relatively easy second moment calculation that actually, or a bit like a law of large numbers, that this thing, I mean, in the limit, it does not disappear like it should, right? I mean, if this were just a normal, if xi were a measure, then this term on the diagonal should disappear, and you should just get this. Only this one should match. Okay, if this were a non-atomic measure, then this should disappear, but here it does not. And so this here you will get actually deterministic limit, which is that. Okay. So in a sense, this cutting out of the diagonal and the construction of this iterated stochastic integral was convenient because it gave us an isometry property for variances. But of course, the price to pay is that we don't really have a Fubini, if you want this kind of Fubini theorem. If you want to apply this if you want to take the product of such integrals, then you have to cut out these diagonal terms and see that they behave differently. And this is really going to be actually one of the crucial, anyway, it's crucial also in the Gaussian analysis that you have this, but it's also going to be extremely crucial to mimic this in the discrete world. And I'm going to show you that tomorrow, how this is done. Paul, sorry, once more, is that okay? Or is this?
Yep, we're still good.
Let me perhaps ask the audience, is this something that you all teach your undergraduate and you're asking yourself, why am I explaining this to you? Or is this something that is actually interesting?
Interesting to me. We're getting nods for interesting, I think.
Sorry, Paul.
Just in case other people are afraid to speak up, this is Luigi. So I'm PhD plus 15, and I've never seen this before, but I'm really enjoying it.
Excellent. Okay, I'm really sorry for insisting on it, but it's just making me really feel awkward that I'm feeling I'm talking to myself, and anyway, good. I don't really like talking on Zoom to an audience that I cannot see. That's just me, sorry. Okay, so
we'll shout at the issues.
Sorry?
We'll speak up if there's problems. We'll shout at you. It's okay.
Yeah, so please shout at me if I'm being too slow or being too slow or too fast.
Yep.
Where there was something in the chat. Okay. Not sure undergraduates will register. Okay, thanks. So I'm sorry for insisting on this a little bit. Okay, good. So you get this kind of behavior, and actually you can. So this is just a summary of what we had here. So if you take the first iterated integral if you take just a simple stochastic integral and you square it, then you get this double stochastic integral, but then plus this diagonal term where you have to take this L2 norm. So this is, what I've written here is just exactly this, right? So this is, I use this formal decomposition where you write this double stochastic integral, pretending that these were measures, which they are not. And now there comes the important exercises. To do this, of course, for arbitrary orders. So, for example, if you did this with a cube, and we're going to do this with a cube, then what you will get is indeed, as you would from a naive Fubini, you will get this the third iterated integral, and then you will get also a term again for contractions, but for contractions where you only contract two variables, and then you will get. So for contraction of two variables, you will get such an L2 term again, but you have to multiply it just by a single stochastic integral. And now the harder exercise is to get such a formula for general n. And the hint is here that you should get something with Hamid polynomials. And the last exercise that I have here is that of course, Brownian motion should be a special case of this white noise. And so iterated integrals are actually a special case of this. So if you, for example, just take the stochastic integral with a deterministic kernel and you square it, then by Ito formula, you will get here, this iterated Ito integral. And I've got this factor 2 here now because I don't integrate. Right, in my original formula, I integrate in a sense over the full space, but this iterated Ito integral, instead of integrating over the full space, I only integrate over this lower triangle here. So this, and in order to compensate for that, I have to put a 2 in front. So I get this iterated integral, but then by Ito formula, you get this extra correction. So in this special case, you actually learned this in your course on stochastic calculus. So it's not something so extremely surprising. So this is actually all I wanted to tell you. I'm sorry, I'm really being a bit quicker than I had thought on this one. So perhaps if there's questions at this point, this would be a good point to ask them. If there's not, then I will just...
I have a question.
Please.
It's Luigi again. So this whole story for Z was somehow supposed to have... you're supposed to then do it for this X gamma or this...
Yeah.
So is there can you tell us a little bit about that? I thought this was supposed to feed into some sort of error estimate.
Well, right. So I mean, at the moment, I'm just trying to I mean, let me tell you a bit how this works in the grand scheme of things. So if you, I mean, I told you that what we're aiming to do at the moment is to just get these kind of bounds, right? This was the target that I had, kind of the intermediate target that I had told you is this is the object in the continuum where you I mean, this is without the delta. I wanted to prove the convergence of this. Well, okay, I'm letting that go even further back. So I wanted to get this kind of statement, right? I wanted to get that this convergence of this regularized object converges to this not regularized object uniform in the gamma.
Right.
And so the analysis of this kind of convergence goes through this perturbative expansion, and the objects that go in there are exactly the z cubed, the z squared, and the z cubed. And so I would really only need to prove convergence, if you want, of the z minus z delta gamma in the correct way, and then according the same thing with the square and this cubed. Okay. So this is what I told you. That this analysis for regularity structures that you have this probabilistic step and the analytic tool. And I only wanted to show you stability in the probabilistic step.
I see. Okay.
Which is actually the more interesting for us. It's also actually the slightly. I think it's the more interesting step for this particular problem. And now I have actually simplified even one step further. And I've said, well, let's not actually prove that I have the stability. Let's just prove that I actually have uniform bounds on this object.
Right.
So this is, but again, this is the technical core. This is the hardest part of the problem. Once you have that, then you regularize and you get stability. It's not very hard.
I see.
So this is the technical core. And what I have now, what I've not done, I've shown you the technical tool that we need to do this in the Gaussian limit. And what I want to show you tomorrow is how to replace this Gaussian analysis by an approximate Gaussian analysis if you have jump martingales. So my plan for tomorrow is to conclude this Gaussian analysis. And I should have really done this now. I'm sorry, but I just thought that I had way too much material. And so I didn't actually prepare the slides for the last bit, sorry. Yeah, so I'm going to show you how you conclude this the stability in the Gaussian case, and then I will give you an idea of how to do it for the jump martingales tomorrow and why it's still true there, and in particular what is a bit harder than in the Gaussian case where extra work is needed.
Okay, cool. Thanks very much.
And let me just anyway show you my conclusion slide, which is here. So the strategy of proof now for this this convergence of Kac-Ising was this diagonal argument where we introduce this auxiliary parameter delta, and then that reduces it to proving stability, pathwise stability of these things uniform and gamma as the regularization parameter delta goes to 0. And this is of course kind of geared to feed into what is needed by the theory of regularity structures. And this by itself now consists of two steps, that you have this perturbative expansion for the solution, and then you use analysis to bound some remainder or some error term. And so what we want now, what's the agenda, is we need to mimic this perturbative expansion on the level of the Kac-Ising, so the perturbative expansion that we do on the Gaussian level. But I want the aim of the end of this lecture today was to show you how this perturbative expansion works on the Gaussian level. So right, I mean, it's if I want to show you what I want to mimic, it's often good to show you the original first. So that's what I wanted to do. And so the main technical tool here is this decomposition of, if you have a Gaussian probability space, you can always write it as a in this Wiener chaos decomposition. So you can always write, if you have a probability space over a white noise with respect to some measure, you can write all L2 variables in this decomposition. But in particular, in this particular analysis where everything is a polynomial, everything is very explicit. And so I've shown you just basically the tools, how you work with these iterated integrals, in particular in which sense Fubini's theorem doesn't hold, and how it is with all these contractions. And so tomorrow in the final lecture, I want to show you how to do this with the approximatories and with almost Gaussian things. Yeah, there's a hand in the chat.
Yeah, so okay, this is a naive question, but I guess, so you talked about all these Z's being approximated, and so this lecture basically covers that. But supposedly that there are some coefficients in front of that, right, like the counterturn and so on. So you also have to show these coefficients converge, correct?
Well, okay, I didn't tell you really what you do in the second step of the theory of regularity structure. So I mean, I can tell you in a minute roughly how this is going to look. Let me. So in the continuum thing for say phi for 2, what you do is you want to solve this equation equal to minus phi cubed plus psi, and you can't because things are too irregular and you have these counter terms and you don't. And so what you do is you say, well, okay, let's look at this dt minus Laplacian z is equal to psi. And then we're just going to look at the equation for the remainder, which is phi minus z. And then that solves just minus phi cubed because the worst term has canceled. Right, this has canceled. And we are going to rewrite that in terms of v. So we're going to write that as a minus v cubed plus 3v squared z plus 3vz squared plus z cubed.
That's 3, yep.
And now it comes in handy that we have probabilistically constructed all these objects. That's why I've done it. And at this point, we're in good shape because, okay, we have to renormalize that, and I'm going to brush that a bit under the rug. Perhaps I'm not, okay, I'll show you that in a minute. But let's just, so this analytic bounds that we have tells me that I actually control this in a space of regularity just below 0. C0 minus, C0 minus. So this was this log behavior that I had shown in this estimate. And I'm brushing under the rug a bit that I need some Kolmogorov type criterion that tells me that this covariance on the level of this regularity on the behavior of the variances translates into really pathwise behavior. But okay, that's also fine. And once I have that, I can forget all about probability theory and just say, well, actually, this is now a nice equation because I can just do parabolic regularity theory that tells me that the heat operator improves my regularity by 2. And the only other analytic rule that you need here is that is a multiplicative inequality that if you have a function f times a misdistribution g, and if this is of positive regularity C alpha and this is of negative regularity C beta, then you can bound their product in C minus beta as long as you can do that as long as the sum of the regularities is strictly positive. Otherwise, you get resonances, and it doesn't work. And but now we are well in this case because this is just below 0, and we can solve with this rule that heat operator improves 2. We can just do a fixed point problem in a space of almost 2 derivatives. And so at this point, we're well and comfortable in a world of fixed point problems for elliptic equations in really reasonable spaces, and we can forget. And then we leverage the stability of this kind of analysis, right? I mean, this kind of parabolic, these parabolic problems. If you set them up this way, you have stability in all the data for free. And so the only thing that you then need to show is really the stability on the level of these expansions, and that's the calculation that I showed you. And so this is how it is in 2 dimensions, and in 3 dimensions it's more tricky. So so what I've just shown you in 30 seconds is this Prato de Bush argument that was in their paper by 2002, 2003 or so. And so going from 2 to 3 dimensions is now you need to go to the real theory of regularity structures.
Thank you.
Yeah. So I mean, that's what you need to do, but it is really the input, the real input that you really need to check at the end of the day is just just these moments estimates here on Z. Any more questions?
Yes, I have a question. When you have discussed iterative stochastic integrals, you work with psi, a white noise on the measure space E with measure mu. And then when you have introduced the bosonic top space, there was L2 of omega.
Yes. Oh, sorry. Omega is right. I should have said that. So omega. I mean, of course, I have my white noise psi, right, which was indexed by this f for f in L2 mu. Sorry, for f.
A mu is defined on E.
Mu is a measure on E.
Okay.
But now, I mean, these things here, these are all Gaussian random variables, and they have to live on some probability space.
Mm-hmm.
So they live on omega.
Okay.
On omega, and let's say the filtration F is generated by all these sigma F, okay?
Okay, thanks.
And so then, but when, I mean, what all of this says, I mean, this is a kind of a very abstract way of saying that any random variable, which is a function of this underlying Gaussian noise, can be written as a sum or as a series of iterated stochastic integrals like this.
Okay, now it's clear. Thanks.
Okay, yeah, sorry for if I was a bit quick in the notation here. Are there more questions?
Not a question. But